Now, what if when you have non-matching meshes? Yeah, I want to import different parts from different, I have different parts in a certain model, but I want to mesh them independently. So I don't want to worry too much about what the meshing is like. Is it exactly matching at interfaces or not? And also sometimes I can have CAD models which I imported and I would just like to use the mesh that is on it. Of course, I have to follow certain rules. I will talk about it later. But there should definitely be a way of doing it because honestly, if everything is about mathematics, then mathematically I can also fool the equilibrium equation to make it believe that all the degrees of freedom at these interfacial nodes are actually matching with each other. That's about one of the ways as to how we do non-matching meshes to work in the finite element domain as well. So let's take, for example, two different parts which I just want to make them of different sizes. So say I have interfacial parts. I'm not going to specify what they are, etc. But the geometry sort of looks like this. So this is part 1. So it's just some incomplete part here. And this is part 2. Okay. And when I want to create a mesh, then I can be sure that I have part 1 and part 2 are two different sizes. So I sort of created nodes or meshes which don't have to really match with each other. So here I have nodes that were created at locations here. Of course, I have one from here as well. So let me do it for different color. So for part 1, I have nodes that I colored yellow. And for part 2, I have nodes that are colored blue. 1 and 2. That are falling within the part 1. So basically what I want to do is I want to make a relation of these degrees of freedom in such a way that they behave like they are related to each other in some way or the other. Okay, so that's the fundamental principle behind non-matching meshes. Now, the way you do it is a mathematical trick, and that is called MPC, or multi-point constraint. Now you may ask, yeah, this is a new term, multi-point constraint, but I don't even know what a single point constraint is. So yeah, I'm confused. SPC is a single point constraint. This is side knowledge. This is not related to non-matching meshes. Single point constraints are basically nothing but boundary conditions. Because I pick up a point and I say, okay, I'll have a constraint on it, it's fixed, it's moving, etc., etc., etc. Okay, that's SPC. MPC is a multi-point constraint. And it's a very interesting situation. It's a very interesting problem. And that's the reason why we should really spend more time on it. So what we want to do in the basic principle of multi-point constraints is that we have a set of displacement degrees of freedom. Let's say they are uj. They are number of displacements in a system. Okay, and they have some weight function or some kind of constant associated with this displacement at every point. Let's say that the constant is aj related with every displacement. And in terms of multi-point constraints, I want to make sure that the summation of all these of this constant with displacement product for all j should be equal to 0. That is the basic fundamental of multi-point constraints. Okay, so for example, I have node. I have a simple problem. I'm not going to use this two-part problem as an example, but just as a simple problem. I'm going to consider that there is a certain part which sort of looks like this. Okay, and these two corner points of this section, of this 1D section, are supposed to always lie in the same line. That means the displacement function ui uk always have to remain the same. That means if ui moves upwards, then uk also should move upwards exactly by the same amount. Okay. Another situation is if ui moves upwards, then UK must move upward but half distance. This is also another relation that I can enforce. So these are certain conditions I can easily enforce on the system. So the equation in that case would actually look like, for both cases, in the first case, in the blue case, case 1, let me write it with a blue pen, then it's probably easier. So in case blue, where UI and UK have to move together and by the same amount, then I have A of UI minus A of UK is equal to 0, because they have to move exactly the same amount, so they are exactly equal. Yeah, even the direction has to be equal. So you can also write it as UI minus UK is equal to 0. Okay. Then if you have the yellow case where it has to move half distance, then you can say A of UI is equal to A by 2 of UK. That means I can write UI minus half of UK is equal to 0. This becomes another condition or a multi-point constraint. Now this is just two nodes. This is a linear homogeneous condition. But we can have multiple nodes in such a way. We can also just not have a linear relation but a non-linear relation. We can also not have a non-homogeneous relation, because you could have a value not equal to 0 but also equal to some prescribed value. You want it to move up to a certain amount by the diff. And that is the description of a multi-point constraint in a very simple example format. But if I do this, if I want to enforce this condition, there's something that changes. That means if I had a certain number of displacement terms in a vector, so I had something like UA, UB, so on, UI, and then ultimately UK, and now I've enforced a relation which actually makes UI and UK dependent on each other. So I am very tempted to replace one of these values with the other and reduce my problem size. And of course, that is what I can do. But always remember that if I started with a system which had k unknowns, then I also have a stiffness matrix which is k by k. And I also have a force vector which is k, size k, k by 1. Right? So this is the stiffness matrix. And this is the load vector. So in the end, if I'm going to do any manipulation on my displacement vector, the same manipulations have to show up in the stiffness and in the load vector. Yeah, of course, load vector I can just keep adding, removing certain locations, that's fine. But with the stiffness matrix, this is a serious problem. Therefore, we need to make sure that when we are going to use such a condition, we understand what we are doing to the equilibrium formulation. And that's the next rule. So say suppose in a normal finite element problem, you started with a standard equilibrium equation. Start with standard equilibrium formulation. Ku is equal to F. Then you said, I want to apply a multi-point constraint, apply an MPC. What happens? I have a modified, I end up with a modified equilibrium formulation. And that is K dashed U dashed is equal to F dashed. So I have everything to be modified. Now when I solve this, I get as a result the modified unknown displacement vector. And from there, to get the final result, I need to still recover my original displacement vector that was unknown. Okay, so this is the basic principle. Sorry, you start with an equilibrium formulation. So you have a standard equilibrium formulation. Then you apply an MPC, you have a modified equilibrium formulation, as a result you get modified U, and then you get U as a recovery.